And today we will officially, for sure, start. Wow, took 3 letters. That's not really nice.
That's the kind of day it has been.
Contour integrals. This black pen is already dead. Dear, dear, dear. Okay,
Would you like
so
a new pen?
yeah, if you got one that'll work, that'll be
What
great.
color?
Black is my favorite.
You're morbid.
It's true. Matches my pants. That way I can't write on myself. Well, I can, but nobody will know. All right, so we finished. We finished last week by writing down the definition for a line integral, and as I mentioned after we turned off the camera, there was I didn't define it exactly the way I wanted to, only because I had in my head the line integral from our multivariable calculus class, which we'll get to in a couple of weeks here. So let's redo what we did, but we'll do it right this time. We only made one little error, and that was we put a z instead of an s, or an s instead of a z. So the idea is, if you have, let's say, a simple smooth curve. Okay, so remember, simple meant that it's not going to intersect itself. Smooth, right? It's got a continuous derivative, right? And it's and it doesn't stop. All right. So if you when I talk about all these things about having a continuous derivative, of course, what I'm really saying is that there's an admissible parameterization which has a continuous derivative. When I say that it doesn't intersect itself, I'm saying that that admissible parameterization is one-to-one, with the possible exception that the endpoints we meet, it's a closed curve. Okay. And let's say we want to integrate a function over this simple curve, right? The smooth, simple curve. So what we said we do is we're going to give a parameterization of this curve, z of t, and say it'll run between a and b. And so if the orientation of this curve is that way, then this would be z of a, and this would be z of b. Okay? And we're going to partition it. So this, let me call this z0. And what do I mean by z0? I really mean z of t0, where t0 is just a. And then this next point here will be z1. And when I say that, I really mean z of t1. So at the second, or this time equals 1, or well, not time equals 1, but time 1. Okay, that'll give me some point on this curve. Right, and then over here I have z of b, and let me call that z sub n. And when I write that, I really mean z of tn. So I'm partitioning time up, right? So I take a sub b, and I can write a sub, or I can write this. This is t0 less than t1 less than t2 less than tn equals b. So I'm just partitioning the interval a to b up, and then I kind of map that partition onto this curve by applying the function z. Okay? And then the definition over, let's say we'll give a name to this curve, we'll call it gamma. The definition of our integral over gamma, our line integral, is going to be, by the way, this is some function with appropriate properties eventually. Yeah. Right, well, it'll be a limit, and we'll worry about what's going to be limiting there in a second. And there'll be a sum. We'll worry about what we're summing over in a second. And then what will it be? Well, it'll be the value of the function at a point that we choose in each interval. Right, so this point here, that could be z1 star, and this point will be z2 star, and this point will be z3 star, and there'll be a point down here, and that'll be zn star. We just choose some point somewhere in the interval between z1 and z2 and between z2 and z3. And we evaluate the function at that point.
Zi star?
I'm going to use k because I don't want to confuse I with the imaginary I.
No, it was Zi star last time.
Yeah, over the weekend I thought better of it.
Because k is just that much better than I.
And then we multiply by delta zk. What's delta zk? Well, delta zk is just the difference between zk and zk minus 1. Okay, so it's the straight line distance, not the arc length. Right? And that's where we had written it down in real analysis. In multivariable calculus, when you learn the line integral, well, we'll learn 3 different versions of it, and the last one, or first, depending on who's teaching it, is going to use the arc length between the 2 points. But we're just going to use the difference between those z-coordinates. And so what should be clear is here we're going to add up over all of these little intervals. And then what should be happening is, well, the number of these intervals should be going to infinity. But since we have this language of partitions and lengths of partitions, we're just looking for the length of each partition to go to 0. But this is the same as saying n goes to infinity. Okay, so this is the definition for gamma here, right? So gamma should be, remember again, a simple, smooth curve. And z of t is an admissible parameterization of gamma. Now, of course, in the end, we want a contour integral, so we're going to want to extend this definition to contours. But we're going to do that in a very obvious way. Before we do that, let me just write down a few reasonably easy to check properties. And this is going to look awfully familiar to those of you who were in my class a couple hours ago. So, well, first, before I write the property, let me write this down here. I'm very often going to want to just write this symbol, set of symbols, in place of this long expression. As long as everybody knows that we're talking about functions of a complex number z with respect to z, then I'll put this down if it makes the formula look a little bit nicer and doesn't cause confusion. Okay. Any objections?
Is it a capital F or a lowercase f?
That's supposed to be a lowercase f. So the first property is that this integral we've defined is additive. Meaning the integral over gamma of f plus g is the same as the integral over gamma of f plus the integral over gamma of g. So the integral of the sum is the sum of the integrals. If I give you a piece of candy, you can figure out what number 2 is.
The difference of the integrals is the
No, but as long as you mention it, I might as well put a minus up here.
multiplication.
I can pull out constants.
So I don't get candy?
No, but you guys feel free to take a candy. Okay. So if you multiply your function f with a complex number c, and then integrate, it's the same thing as integrating f and multiplying by the constant c. Okay, you can pull out the scalars. Not a big surprise, I think.
It's shocking, actually. I need to leave now. I've learned too much today.
Yeah.
The negative thing, right? Does it with the multivariable ones, right?
Does it multiply? Well, yes, it does, actually. I guess I could mention that. The thing is this is really redundant. Okay, and why is it redundant? Why is putting this minus here really redundant? Well, instead of writing a minus here, I could have just written minus g, which is again going to be, if g is integrable, minus g is integrable. By the way, there's an underlying assumption here that I'm not mentioning. I'm thinking I am. That's what I'm doing right now. I didn't write it. This doesn't always make sense. It could be the case that this integral exists and that these two integrals do not exist individually. Right? For instance, if you just think of the real case. If you integrate, let's just talk over here. If you integrate 1 over x, and you do it from, let's say, -1 to 1, that's not going to exist because you have this really nasty discontinuity at 0. But if I did this, it's not a problem because this is just 0. But if I split this up,
all sorts of things go wrong.
I mean, they don't exist individually. It doesn't make any sense. So this only makes sense when individually all 3 of these integrals exist. And it's just, and the reason why is that, well, it comes from limits. Limits, you can only break up the sum of a limit into a limit of a sum. I guess you just break up the limit of a sum into the sum of the limits. In any case, you can only do that if the individual limits all exist. And by the way you prove these things is you just go back to this limit definition. And it's routine, right? You can do this. There is no, you don't have to think too much to get these to work out. They look just like the same proofs from 165. Okay, the last one is a little bit different. You've seen it before in 166, not 165. But, it's going to look a little bit different here. If you have a simple smooth curve, we have a direction, right? We have this orientation. But we could take the same curve but run it backwards. And if we do that, if we want to take the exact same curve as gamma but run the movie backwards, then the way we're going to write that is minus gamma. So this means we run the curve backwards. And it turns out that if we integrate f over the opposite curve,
Would it be negative?
yeah. And this is the same thing as when you single variable calculus, you integrated from a to b. That's the same thing as if you flip it over, you integrate from b to a, but you have to stick a negative in front. So we have these easy properties. Okay. So let me just say now that, well, if this limit exists, sum k equals 1 to n f ck star. You see why we come up with notation for it, by the way? Because writing this down is just a pain. So if this limit exists, then f we write as integrable on gamma. And there's a theorem which we won't prove here, which is that if f is continuous on gamma, then f is integrable on gamma. So your nice continuous functions are going to work. You're going to be able to integrate. And then that was exactly what we had in calculus. Right? The Riemann integral, the one that you learned. By the way, I call it the Riemann integral in case you don't know, because there are different integrals that exist. You can define integrals in different ways, and they're not equivalent. I mean, some of them are, but they're not all equivalent. And so as you go up higher in this world of mathematics, when you talk about integrals, you sometimes have to say, well, I'm talking about the Riemann integral, or the Lebesgue integral, or the Darboux integral, something like this. Okay, but in calculus, when you had the Riemann integral, you knew that if you had a continuous function, you could integrate it. Okay, so this will be useful. You don't need continuity. There are weaker conditions under which a function will be integrable, but they become more difficult to write down and to pin down. So continuity is good enough for us. What's the next question? Exactly, right? That's the perfect next question. How do you do it? Right? We certainly are not going to evaluate this limits. By the way, are you guys seeing a real parallel between these lectures?
Yes.
Do you think this is all by design or what?
Massive conspiracy
It's a
theory.
massive conspiracy, yeah.
So could we call this a multivariable calculus of complex numbers?
Well, but remember, the multivariable calculus stuff, I mean, that was just all the single variable calculus stuff. It just added an extra variable. But you basically, every time we write down a definition of an integral, right, at least the Riemann integral, it always looks exactly the same. You evaluate the function at certain points, and then you multiply by kind of the width of some region, and that gives you the area of a rectangle, and then you make the rectangles really small, and you make a lot of them, and then you take the limit as that goes to infinity, and the size of the rectangles goes to 0, and boom, voila, there's your integral. It's the same story every time. Okay, so the question is, how do we compute this integral? How do we do it? So in single variable calculus, you have the fundamental theorem of calculus that tells you how to actually compute it. You find an antiderivative and evaluate it on the endpoints. Okay? So it would be nice if we could write down something like that. In multivariable calculus, you appeal to Fubini's theorem, right, which tells you how to break up a double integral, for instance, into an iterated integral. What's that? No, you guys don't know what Fubini's theorem is yet. I know. You have to wait till like probably Wednesday or Thursday, either tomorrow or Thursday. We'll get it.
I thought you were going to say like a long time.
No. Fubini's theorem is on its way.
It's all its way.
So here's, I'm going to tell you the answer. So I'm going to spoil the mystery novel here. We're not going to prove it immediately. We're going to do some things before we prove this. Well, we at least justify it. The full proof is kind of lengthy, and I don't want to put everybody to sleep. I'll just outline a proof of it. In any case, here's our goal. So if our function is integrable, and we have a nice path, right? We have a nice, simple, smooth path. We're going to want to show something. Let's see. Do I do it for? Yeah, I'll do it just for simple, smooth curves. Right. So if z of t, where t goes from a to b, is in, let me abbreviate, admissible parameterization of gamma, right, our simple smooth curve. Right? And f that is integrable on gamma. Then integrating f over gamma is going to be given by actually just what looks like a definite integral. In fact, it is. It's an integral for over a real variable, namely t. Right? Remember, t here is just running between a and b, and these are real numbers, a and b. You're going to integrate from a to b. The function f, and what are you going to put into f? Well, you're actually going to put in z of t. Okay? So z is a function of t. It's a complex function of t. It eats in a real number, but it spits out a complex number. And then you're going to multiply by the derivative of your parameterization z. And then this thing is taken with respect to t, right? You're integrating with respect to t. Okay, so this is kind of a funny looking formula. Once we go a little further in multivariable calculus, this formula will seem less weird. I mean, you'll see it pops up in a few places. And when I justify this statement, you'll see how it comes out. It's not all that peculiar, but okay, that's the way it's going to be. Now, there's a really nice observation that you can make once you know that this is the answer. All right, so I'll tell you that's the answer right there. Okay, so you don't need to turn to the back of the book and find out who done it. He done it. So here's the really cool observation. Okay. Note here I said let z of t be an admissible parameterization of gamma. And then I said if you compute this definite integral, you will get the integral of f over gamma. Now, let's say I had chosen another admissible parameterization, because we've seen already that if you have a curve, you can have more than one parameterization of it. So I choose a completely different parameterization, the a and b might change, and I compute the integral for that parameterization. Since this is supposed to work for any z of t, then you should get out, again, the integral of gamma. Which means it doesn't matter what parameterization you take. You always get out, right, the same answer. So this equality is not up to choosing z the right way. It just has to be any parameterization. So this formula, and by this I mean the one over to the left, this formula for the integral of f over gamma is independent of which admissible parameterization is chosen. So this is an important sort of theorem in mathematics. Whenever you define something where you make choices, you like to then be able to turn around and say, it doesn't matter what choice I make. It's sort of like, if there's a boy and a girl and they really like each other, and it really shouldn't matter. He has to wear some clothes to dinner, right? I mean, it would be pretty awkward if he didn't. He has to wear some clothes to dinner, but if she really likes him, it shouldn't matter what clothes he wears, right? Should be independent. Her love for him should really be independent, right?
It depends on where they meet.
Yeah.
If she really loved him, if she really loved him, she would
Completely
care
agree with
about
that
one.
Like here, I really.
All I'm saying is that it shouldn't be so peculiar to go to your, girlfriend's parents' house wearing a penguin costume. Okay, that should not end the relationship. That's all I'm trying to get at.
Might make it non-continuous.
All right. Well, let's try to do an example. And this is actually a pretty useful example.
That's great.
So I'm going to give you my path. So first, my gamma. I'm not going to write it as gamma. I'm going to use the suggestive title C sub r. And C sub r is not the cyclic group of order r, for those of you in 267. But this will be this will be a circle of radius r. Yep. And then I'm going to put a little z sub 0 down here. That tells you the center of the circle. So there's some point in the complex numbers, z sub 0. And so here I have a circle with radius r centered at z sub 0. And, well, the way you might write that down is, this should ring a bell or two.
Who's Belle?
I believe Belle was the love interest of the beast.
No, I mean, who's... Which bell should it ring?
All right, so you might recall that the way to write, the quick way, complex analysis is great. You can write down things very short amount of space. The circle with center Z0 and radius R is just, that's just the formula for it, right? This tells you, remember when you do the norm of a difference, that's the distance between the points. So this is the distance between Z and Z naught is R. Oh, well, pick here on Z naught, and all the points that are R away, no, that's a circle. Yeah, okay, cool. Fine. I want to integrate over gamma the function Z minus Z naught to the n, where n is any integer. I want to be able to answer this for any integer.
Oh, did you hate?
No, I'm psychic.
Oh, okay, that's good.
Oh, can you remind me that at the end of class that I wanted to tell you something?
Okay.
Because otherwise I'm going to forget, because I forgot and I just remembered right
It's
now.
about statistics.
It's, no, but it's really cool. Good job.
All right, we better remember it now.
Something that I...
Golden. It's odd to write golden in blue. Did anybody read my Facebook and get the joke about the odd bars?
I've never run through you, that'd be creepy.
I went.
Oh, I'm friends with him. But I haven't been on Facebook.
Oh, don't worry.
I
I'm
took
gonna
my
friend
kid.
everybody.
I took my older son to gymnastics, and I turned to the mother sitting next to me watching, and I said, "Oh, my son's on the odd bars." Nobody. No, she definitely didn't get that joke. Apparently, you guys aren't getting it.
The uneven bars.
Yeah, exactly.
Oh!
2n minus 1
Oh,
bar.
I got it. I just didn't think it was that.
I guess the way home
It
I
just
knew what
sums
the
up
bar
the joke
was
really
really
well. I was
called.
like, got it. I just didn't think it was that.
So, the first thing we have to check, if we're going to use this formula,
That's nice.
we have to make sure that our curve is a simple, smooth curve. Okay, well, it's a circle. Right? So, is that necessarily simple and smooth? Well, see, smooth, okay, this is not going to be such a problem. What about simple? Simple means that it doesn't intersect itself. But a circle does intersect itself, right? It comes together. Right.
But only at the end point.
Only at the end points, unless you go around the circle twice.
It's not.
So we better say that we're, right, so we traverse gamma, or we'll say C. I don't know why I keep writing gamma there. Well, I guess it's shorter, that's why. All right, so we'll traverse gamma once, and shall we do it in just the positive orientation direction, counterclockwise? Okay, once in the counterclockwise direction. Okay, so we have to specify that, because if you went around twice, it wouldn't be a simple curve anymore. It wouldn't be a huge problem, but it would be in the world of contours instead of smooth, simple curves. And by the way, so since this is actually a closed curve, we do a special symbol. When we do the integral, we put a little circle around it. You can do this even if it's not a circle, as long as it's closed when you do this. And if you really want to be clear that which way you're going, we can write this little arrow to tell us we're going in a counterclockwise direction. So now you know what that symbol means, right? You've probably seen that in the books.
Yeah, I've seen that. It's a really cool symbol.
Isn't it?
Without the arrow, though, the arrow just kind of screws it up.
Yeah. So in text, by the way, you can do
Those
slash
look like balance.
OINT. That'll do it. Point. I always think oink when I write it. Okay. So how do we do this? Well, if we're going to use this formula, we need an admissible parameterization. So we need an admissible parameterization for gamma, which is a circle of radius r centered at z naught. All right, so how did we write down a circle? What was our parameterization for it? Say just the unit circle.
Unit circle was e to the I pi t. E to the 2 pi I t.
E to the 2 pi, so if...
from t equals 1, or from t equals 0 to 1.
would that work?
Yes.
Probably would work, but there's an easier way. Which is e to the it, just drop the 2 pi.
Oh,
Yeah.
from
And just
to the end.
run from 0 to 2 pi. Okay, how would we make it radius r?
Multiply by
R.
Yeah, right? If this is radius 1. If you multiply by r to all the points, they just get shot out by r, so they're down to radius r. Okay, so if there was no z naught to worry about, you just had a circle of radius r centered at 0, it would be re to the it, where t runs from 0 to 2 pi. How do we shift it over to z naught?
Subtract z naught.
Almost.
Add z naught.
We add z naught, which is actually, it's what we had to do on this problem last week on the homework, where you wanted to show that e to the z was 1 to 1 in any neighborhood of any circle of radius 2 pi.
Yeah, I didn't do that one.
Okay, good to know. Yeah. Okay, so our parameterization.
Sounds familiar, but I didn't do it.
Okay. We first build a circle of radius r. So here, t runs from 0 to 2 pi. So that goes around once in the right direction. If I wanted this to go in the opposite, right, the clockwise direction, then I should probably go from what?
0 to negative 2 pi.
0 to negative 2 pi. That would go in the opposite direction. Okay, so this gives me the circle of the right radius, but to move it over to z naught, I just add z naught to it. And to make sure we're starting in the right place, we'll if, for instance, t was 0, then this just becomes e to the 0, which is 1. So you get z naught plus r. Oh, that's good, right? Just to start at z naught and go over by r.
So this one's like 2b on homework?
I don't have them memorized by number, unfortunately.
Were you supposed to take this?
Yes, that is exactly
So
the right thing.
you
Yeah.
would add or subtract? I subtract.
Well, you need to add, because what happens if you subtract? You'll end up at negative z naught plus r. So you'd be at the circle centered at negative z naught.
No, well, I mean, here.
I mean, that's right.
So
That's saying the
that
distance
goes
between...
That would make
Yes, it would shift it up to 2i. That's the same.
Sorry, I had trouble picturing that for some reason.
Okay, so we found an admissible parameterization, right, which is usually the hardest part of these things. Okay, and now we can apply the formula. So the integral gamma of z minus z naught to the n dz should equal the integral from 0 to 2 pi. We're going from a to b. A to b are the endpoints of the parameterization domain. We go 0 to 2 pi. Now we have to take f, which is our z minus z naught to the n, and evaluate it when z is actually z of t. But we know what z of t is. It's z naught plus re to the it. So this is, okay, z becomes z of t, which is z naught plus RE to the IT. And then we have to subtract Z naught. And we have to raise it to the N. Okay, and that's the first bit. And I'll pause for questions. Make sure you believe that's how you plug it in. You might be thinking, wait, where do I put it into where? Okay. Our function, f of z, is z minus z naught to the n. Z naught is a constant. Okay, that's not going to change. If I plug in for z, z of t, that means everywhere I see a z, I have to put z of t. So here I took a z, and I turned it into z of t. Now we got it. Okay, so that's the first part. That's the f. The second part, I need to take the derivative of z.
Does the chain rule apply?
Of course. Of course.
So the chain rule works.
So what's the derivative of z? Of t? Well, let's see. That's a constant. That goes away. And then this one is going to be, well, by the chain rule, derivative of this is I. And remember, we're taking the derivative with respect to t. So I r e to the it. I r e to the it. And then we have to integrate with respect to t.
Oh, is that what goes on?
Okay, well, there's some nice things going on. For starters, you have a z naught minus z naught. That will help. And then you just take r e to the it to the n. Well, that just raises this to the n and the r to the n. So you have 0 to 2 pi, r to the n, e to the I n t. And then, let's see. Oh no, I have another I. That I can actually pull out. So I'll put the I out. Actually, I can pull all the r's out too, can't I? Because they're not, I mean, those are constants. That's really, let's pull all those r's out. And how many are there? There was an r to the n, and then one more r. So it's r to the n plus 1. And then I just have e to the I t, nt, and then another e to the it. So it becomes int plus it. I r to the n plus 1, 0 to 2 pi, e to the, okay, let's see. When you put that up there, you get, you can pull out an it, and then you get n plus 1. So it'll be I n plus 1 t dt. Which does not look that bad, actually. It's an integral. It's just integrating a power of e, a linear power of e. That we should be able to do. So let's write this up here again. I r to the n plus 1 integral 0 to 2 pi e to the I n plus 1 t dt equals, okay, what do we got? I can copy the constant. What's the integral of this thing?
Can you just pull all that R?
Sure, it's a constant, right? It's a constant radius of the circle. Well, I made it, so the way I first I raise it to the n, I get r to the n, and then I pull it out. And then I have one more r, and I pull that out. So you get r to the n times r, which is r to the n plus 1. So this gives you n of them, and this gives you one more.
So the integral of that.
No, I mean, these go away. You get r to the n. These are all multiplied. Everything's multiplied together. So I have, when I combine all the r's, I get r to the n plus 1. So you pull it out because it's not a function of t.
So the integral of that e part
Huh?
is that e divided by I times n plus 1. And so the i's cancel.
The i's cancel.
Yes.
Okay. So, right, this is also always the case, just on the side. If you integrate e to the ax dx, this is always 1 over a e to the ax. C, of course. Okay, so, and then of course we have to evaluate 0 and 2 pi. Okay, by the way, is what we just wrote down always true? Yeah, is this equality, is this always true? Remember, n is any integer.
No,
What's the problem?
it's not true at
Negative 1 is a problem. Okay, so let's just put that on the side here. N not equal to negative 1. We'll figure out what happens to negative 1 later. Okay, so assuming n is not negative 1,
CLN.
we'll see. We'll see what happens. I don't think it's so hard. We'll see. It'll be okay.
No, I can't see, I'm blind.
All right. So when n is not negative 1, you can do this. And let's see, the i's cancel. And then we have to evaluate at 2 pi and at 0. Okay, but what happens when we put a 2 pi in for t? You get I n plus 1 2 pi. Now this is a multiple of 2 pi, right? N plus 1, n's an integer, so n plus 1's an integer. What is e to the 2 pi I n?
Same as 0.
E to the n.
When you, right, any multiple of 2 pi is, well, it's right back there, right? And what's the coordinate right there? It's 1. So when you evaluate this at 2 pi, this whole thing is just going to give you 1. And what about when you evaluate it at 0? It's e to the 0, which is 1. And then nothing here changes, right? There's no t over here. So you're getting something times 1 minus the same thing times 1. And so this is just, you know,
0?
it's just 0.
Oh.
So you did this whole thing and look at the answer, you get a 0.
You like it when we do that.
Isn't that fun? Okay, so what about when n equals 1, or minus 1 rather?
Then we have to, that's the log function.
Well, let's see. When n equals minus 1, I r to the n plus 1 integral 0 to 2 pi e to the I n plus 1 t dt equals, well, let's see, n is minus 1. So you just get I r to the 0, which is just I. Integral 0 to 2 pi. N plus 1 is 0. So you get e to the 0, which is 1. So you're just integrating dt. That's not even the log function. It's just all gone. Okay, and we saw today what happens when you integrate just 1. It just gives you the length of the interval, right? It's just 2 pi minus 0, which is
2 pi?
2 pi times I. So 2 pi I. So in the end, we get that if you integrate around a circle one time in a counterclockwise direction, z minus z naught to the n dz, that when n is not equal to minus 1, you just get 0, and when n is equal to minus 1, you get 2 pi I.
Is that the same way you go clockwise?
So what would happen if you go clockwise?
You
Well-
get 0 and negative 2 pi r.
Yeah. So we already have this property 3, which says if you traverse a path backwards, then you just have to negate the answer. Okay, another question you might ask is, what if you went around twice?
0 and 4 pi.
Yeah, that's the right intuition. That you just add it up. And that's true. If you go around twice, you get 4 pi I. If you go around 3 times, you get 6 pi I. Each time you go around, you just collect the same values, basically. So they don't always have to be 0, even if you go around in a circle. But most of the time, you see it is. This is actually not a coincidence. It's more surprising that you get a 0 when n is -2, -3, -4. In light of a theorem I'm going to show you later on, it's not so surprising when n is 0, 1, 2, 3, 4, 5. Right? Namely, Cauchy's integral formula is just going to say, oh yeah, it has to be 0. You don't have to do any computation at all. All right. Okay. Any questions about this example? This is a useful example to just remember the answers to. This thing pops up, sometimes by itself, but oftentimes as part of bigger problems, where you basically try to kill everything else and reduce it to this. So that you can get this. And you're going to see a lot of answers that have a 2 pi I in them, which is one of the reasons why I think that pi should be 2 pi. Yeah. Okay.
I always thought that too, actually.
Where do we use the diameter of a circle? We only ever use it when we're defining pi. Everywhere else we use the radius. Circumference divided by radius is 2 pi. That's what it should be pi.
It should be. I always thought so too. Glad we agree on something.
Sorry, the convention was established probably before this math was.
But it's never too late for a change.
Of course it is.
We should evolve.
Someone told me that if we based our number system on E, that it would be a lot easier. Or something like
It's
that.
harder to count on your fingers in base E, but...
No, I mean like if the whole thing was based on E, it would be easier. I don't know, that's what I heard. Someone told me that.
You know,
It'd probably be easier at this level.
you know, a long back, maybe it was back in the 70s, people were right. There's a lot of literature that was suggesting that we switch to a base 12 system. There were books about how are we going to teach our students, how do we teach adults, all these things. I've read these books, I saw them in the library, I was amazed. The idea being, 12 has so many factors, it's so much easier to do computations, whereas 10, 2 and 5 are the only factors. Most decimal expansions, for instance, in base 10 go on forever, whereas in base 12, more of them terminate. So, that's not so bad.
Interesting.
E, this is a little harder to see as a good counting base.
But like they say, like that, like natural things. Well, maybe not. Maybe that's
certainly
not
E
a
shows
good way
up.
to do it. But like for instance, if you put water in a tub and then you drain that and and then you time it and you divide that number by E, you'll get like a whole number or something like that.
I'm not sure about that, especially
I
given...
haven't tested it.
Well, especially given the way my kids throw water out of the tub, I think that would screw some things up there.
I don't know.
Container, right?
That's what I heard.
These poor people who live beneath us have water dripping on their heads, I'm sure. Okay. So...
I'm sure they do their own.
No, I don't even know the people who live beneath me. So let's talk about contours now. So this is basically as far as I want to push just for a single smooth, simple curve. Now let's let gamma, capital gamma, be a contour. And remember what this meant is a contour, it could be a single point, but it's a collection of smooth, basically it's a piecewise, smooth, simple curve. Right? So each one of these is smooth and simple. And their initial and terminal points line up right.
Is that a capital gamma?
That's a capital gamma.
Let's say it looks like you're playing Hangman.
Almost.
Is that where Hangman
So
comes
this will
from?
be I don't believe so. I'm guessing hangman comes from when they hang man.
Really?
That's so strange.
Okay,
Why
so
would they ever think of that?
we're going to take a contour, and I want to define the integral of a function over that contour. And I'm going to do it in sort of the most obvious way. I'm just going to define this as the sum of the integrals over the pieces. And then, well, in case you were paying very close attention to the definition of the contour, where I said it also could be a single point, I'll define that equal to 0 if gamma is a single point, which is a reasonable definition, I think. This is just to handle some cases maybe later on down the road that we use. So let's see, I think I want to do an example again. Oh yeah, so well, I'll just say given this definition, then it's clear what we should do if I want to do the following. Okay, I'm going to define a contour. And it's just going to be, well, take the circle radius r centered at z0. And we'll go, it's just the same one as before. And we'll just go around it counterclockwise. And then when you get back to the beginning, do it again. So we're just going around twice. And take the same function. And what this definition tells you to do is, well, you just integrate it once, the first circle, and then integrate on the second circle and add up the answers. And we already talked about this. So you should get 0 when n is not minus 1, and 4 pi I when n is minus 1, because, well, on each one you get a 2 pi I. So when you add them up, this one 2 pi I, this one 2 pi I, that 4 pi I. Okay, so that's not a terribly lightning example since I already talked about it. Let's do maybe a slightly more interesting one, which will, well, at least we'll get to start.
Don't erase that. It's important.
I just used erase as the past tense of erase.
Yes, I heard.
I almost erase it.
Gross. Is that even a word?
No. Well, if it is, it doesn't mean what I thought it meant. All right, so I'm going to draw a little contour here.
This is R. It's R. That's just R, comma, Z0, comma, C. So R.
It's just the same thing.
Yeah. Same thing.
Like,
Just pat yourself.
yes, I sure did.
You're proud of yourself.
I am always proud of myself. Okay, that's a lie.
Okay. So, is it clear what my path is?
Only if you erase it.
Yeah. I'm going to start at 0, sorry, and go around. So this is not a smooth, simple curve. It's simple, but not smooth because.
Piecewise.
Yeah, but it is piecewise, right? These corners here are bad, but okay, that's okay. We're allowed to do that.
Can you say it's piecewise smooth?
It is piecewise smooth.
Sweet.
And so this is actually a contour. Right? Because it's a piecewise, simple, smooth curve, and so I can call this gamma 1, then gamma 2, and then gamma 3, and then capital gamma would be gamma 1, gamma 2, gamma gamma 3. And the end, the initial points and the terminal points line up in the right way. We're in good shape. Okay, and so now the question is, what if I want to integrate a function over gamma? For instance, how about the conjugate of z squared? That's a perfectly reasonable function to write down. And we'd like to integrate this thing. What's the first step? Well, in the end, I want to use a formula. Right? I want to use a formula that says that integrating gamma over gamma, integrating f over gamma is the same as integrating f over each of the individual gamma 1, gamma 2, gamma 3. And then for any individual one, I want to use this formula that says that once I choose a parameterization, I can integrate it using that formula. That's what I want to do. Right? Wow, you look like I said something completely random. Okay, which part is random to you?
It's not. It's just that if we have to do it so many times, that means we have to do it so many times.
Yep, yeah, you have to do it 3 times. That's exactly, okay, so it wasn't random, it was just horrifying.
Wait, so how did you get the z squared thing right here?
I gave that to you. This is I'm giving you a function.
Oh,
Yeah.
okay.
So this is the interesting thing. There's 2 things that you have to deal with at the same time whenever you're doing these contour integrals. You have to deal with the contour, which by itself is going to have parameterizations and all sorts of that fun stuff, and you have a function lying around. And you have to keep them both in mind. And there's, I mean, the contour that I write down, it doesn't tell you anything about what functions are defined on it.
Right.
And I have to give that to you as a separate piece of information. I could have put a completely different function in here. It's the same way that knowing the interval over which you're integrating, a to b, in single variable calculus doesn't tell you what function is lying over a to b. I have to give that to you separate. Okay, so this we can do. That's not a problem. We can just break it up. It already tells us we're going to have to do this 3 times.
Which isn't really that bad considering their parameterizations are pretty easy.
Okay, so we need parameterizations, right? That's going to be the thing. For each one of them, we need a parameterization. So let's find parameterizations. So for gamma 1, what is going to be a parameterization for this thing? Well, let's see. It's going to look like z of t equals something. And let me call it z1 just so that in the end we don't get confused with our z's. So it's going to equal something, and then we're going to have to write t less than or equal to, and we're going to have to put stuff on the ends. So how do we parameterize this line segment from 0 to 2? You have an idea?
No, that's what I don't know how to do.
Ah, so this is the hard part, right? Okay, it's good. That's why we have homework on it this week, huh?
Can we just say t from 0 to 2?
Yeah, sure, why not? We want it to go from 0 to 2, so we'll put t down from 0 to 2 and then just copy whatever t is. Okay. Is it an admissible parameterization? Sure. Its derivative is 1. That's continuously differentiable. It doesn't stop anywhere. So, okay, good. Okay, maybe the next one's a little harder. Let's see. So gamma 2, we'll call it z2 of t equals, and again we're going to need a t between something and something.
2 plus ti z or from 0 to 2.
Now let's see. When t is 0, you get 2, and as t goes up to 2, yeah, sure enough, it just follows this path, right? Okay. Good, good, good. Okay. How about gamma 3? We'll We'll call it Z3 of t. We'll presume to know what the answer is. So now we want to get from 2 plus 2i down to 0. Maybe this is the hard one, right?
About t plus ti.
T plus ti.
Or t. Yeah.
All right, and what would I let my things go between? Well, actually a little bit of a problem there, right?
Yeah,
Because
I know, because
we
it's
want to start it
backwards,
at 2
right.
plus 2i. What if we, what if
What
we
if
went from,
We did.
2 plus 2i minus t plus ti.
What's
Well,
that?
it's like this one, right? Just
I don't know, I
you
don't have
get it?
supervision. Well, you can tell me what you see.
Essentially.
Essentially, yeah, so we're going to minimum.
Well, I mean, you could do this. What if you put a minus here,
Right, minus.
and a minus
Yeah.
there, and then you ran from -2 to 0? Then when, would that work? When t is -2, you get 2 plus 2i, and all the way to 0 where you get 0. That would be one way. Of course, as
So
we
you don't have to
know,
have t from 0 to 1, or 0 to 2, or 0 to anything.
it could be anything you like. There are different parameterizations, right? And the theorem that we wrote up at the race now said, that was our observation, it doesn't matter which parameterization you take, you get the same answer out of it. This is important. Okay, so I think, yeah, we're at the end of our time here. So tomorrow we'll pick up and we'll finish this computation. There's a lot to it, of course. So we'll go through it and review it. But you can see already, we've actually done all the hard work. Right? Because now we just need to write down 3 different integrals. And, well, we're going to have to plug these parameterizations in for z. Okay, do that and then take derivatives. Derivatives are going to be very easy. And then we'll have to integrate. Okay, that's some work, but it's not so bad. Okay, and yeah, so we'll do this example, and then the next thing we'll do is actually justify this formula. So I will give you at least something resembling a proof of it.